We're going to have a look at molecular polarity. We're going to look at the polarity of the following VSEPR shapes: linear diatomic through tetrahedral. It could be really handy to have your flow chart. Basically, the take-home message is a symmetrical molecule is nonpolar. Alright, so we're going to start with linear diatomic, so the simplest of all the shapes. This is where we have only two atoms involved in a covalent bond, and the two atoms, the shape of them is a straight line. So consider H2. The electronegativity value for both atoms would be the same, so this is of course going to be called nonpolar. HBr, right, hydrogen and bromine are different elements, therefore they have different electronegativity values. We can go look it up, the actual values, but we'll find that bromine is more electronegative, so I use the delta negative symbol on bromine and delta positive on hydrogen. It's a polar molecule. Basically, the atoms are different. It's a polar molecule if they're the same, nonpolar. From there, we're going to look at what's called linear triatomic. This is where we have three atoms that also make a straight line. Two examples that I'm going to draw on are HCN and CO2. So I'll draw the Lewis structures. Right, you could draw the Lewis structures, use the steps to get them, but here they are. I'm going to put the electronegativity values in here. I'll just write them all essentially on the same line. Hydrogen's value is 2.1, carbon is about 2.5, nitrogen is about 3.2, oxygen is 3.5, while carbon is 2.5. Now, I can go around and I can assign polarity arrows to each of the bonds, and I can say, okay, well, both the carbon-oxygen bonds are polar, but they're actually polar in equal yet opposite directions. So effectively, the polarities cancel each other out. Okay, I could also look at this and say carbon dioxide is a perfectly symmetrical molecule. It's nonpolar. There's an equal distribution of electrons throughout the molecule. HCN, just by inspection alone, I can say, well, the two bonds coming off of carbon are different because they're to different elements. Okay? This automatically is going to result in an uneven distribution of electrons throughout this molecule. This is a polar molecule. Okay? Unsymmetrical, non-symmetrical, however you want to describe it, is a polar molecule. All right, so we can have a nice little summary line about this. All right, so if both substituent atoms are the same, it's nonpolar. If the substituent atoms on the central atom in a linear triatomic molecule are different, then it's polar. All right, I'm going to move right along to bent. Bent is quite simple. It's always polar. It's always polar due to those two lone pairs of electrons on the central atom. This results in an uneven distribution or an unequal distribution of electrons around the central atom. This is the very definition of a polar molecule. So you can look at any VSEPR shape, and as soon as you've established that it's polar, that it's bent, you know that it's polar. All right. Now we'll flip into trigonal planar. Right, trigonal planar is a flat molecule. So if all three elements or all three atoms bonded to the central atom are the same, all the electronegativity values are the same. The distribution of electrons is equal throughout the molecule, nonpolar. But as soon as I change one of the molecules, one of the atoms to a different element, the bond polarity changes, and as a result, the molecular polarity changes. Okay, so you have to examine symmetrical, trigonal planar, nonpolar, non-symmetrical, trigonal planar is polar. Okay, pyramidal, our trigonal pyramidal is back to the argument from bent. There's a lone pair on the central atom here. Automatically, it's polar because there's an unequal distribution of electrons in 3 dimensions. All right, sorry about why it's writing off the screen a little bit there. I'm not sure. But the take-home message from this is that trigonal pyramidal is always polar. I'll see if I can get this that screen cleaned up for you. Tetrahedral. There's two possibilities. If all the substituent atoms around the central atom are the same, so if they're identical, sorry about the bell there, the molecule is nonpolar. If any one of those atoms is different, then the molecule is polar. So again, if all of them are the same, nonpolar. If any of them is different, then it's polar.